Next, we're going to look at another set of combinatorial classes that we studied in the early lectures. It's compositions and partitions. And that starts out with, we want to count the number of ways to express an integer n as a sum of positive integers. And lots of ways to show that that number is going to wind up being 2 to the n minus 1. And these are the small examples. Let's see how that works with analytic combinatorics. To do it, we start out just by doing the class of integers. The class of integers is a sequence of positive integers of at least one object. This is counting in unary. We did this example. So the generating function for that is z over 1 minus z. So there's a z to account for the at least one, and then 1 over 1 minus z for the sequence of the rest of them, immediate from the symbolic method. And so in this case, there's a singularity is a pole at 1. And this function grows, so it's a little hard to see that singularity, but it's there. So we can compute the residue. Numerator evaluated at 1 is 1. Derivative of the denominator evaluated at 1 is also 1. We just get 1, and the end is we get 1. There's one positive integer of each size. So to get compositions, we just generalize that. A composition is a sequence of integers. And sequence is 1 over 1 minus, so the generating function by the symbolic method is 1 over 1 minus z over 1 minus z, which simplifies to 1 over 1 minus z over 1 minus 2z. Rational, meromorphic, so we're interested in the pole at 1/2 this time, z equals 1/2, it goes to 0. And that's a single pole on the real line closest to the origin. We can compute, evaluate the numerator 1/2 as 1/2, differentiate the denominator, evaluate it 1/2, we get 2, so that turns out to be 1/4. And so the asymptotics, the coefficient is divide those two and get a 1/2, and the exponential growth is 2 to the n, 1 over that. So the end result is 2 to the n minus 1, as expected for compositions. And again, there's certainly lots of simple ways to get that result, but with analytic combinatorics, we can generalize in all sorts of ways. For example, suppose we restrict the size of the parts. How many ways are there to express n as a sum of 1s and 2s? Well, that one also we can prove other ways. That's the Fibonacci numbers, but it's instructive to look at it through analytic combinatorics. So that is a sequence of 1s and 2s, and immediately translates to the familiar generating function for the Fibonacci numbers. And that one, we've done these kinds of calculations in the earlier lecture. It's got its singularities at phi hat and minus phi, and we can compute the coefficient and use tricky Fibonacci golden ratio identities to go ahead and compute the full asymptotic growth. So it's a constant times another exponential growth factor to the nth power, in this case 1.618. But whatever set of things we use to pick to restrict the parts, the same method is going to work. It's just going to be a polynomial, a ratio of 2 polynomials. Here's an interesting one that's covered in the book. How many ways are there to express n as a sum of primes? You might have trouble trying to figure out the asymptotics of this using elementary methods. But with analytic combinatorics, it's just a sequence of the z to the 2 for one factor for every prime. Now, this turns out to be a little more complicated than it looks, and I'm leaving out some details that are discovered in the book, but it is this generating function. It's not quite a polynomial, but it turns out to be an analytic function. And it's quite a strange looking analytic function, and this is not doing all primes. This is only doing up to 11. Actually, there's an infinite number of singularities of this, but they're all further away from the origin than the dominant one, which is on the real line, and you can calculate where that one is, even though there's an infinite number of primes. There's enough space between the primes that it's possible to prove this. And that immediately gives the coefficient and the exponential growth. And again, there's, as with many of these problems, there's going to be some periodic oscillations in next terms, but still it's going to give a quite accurate estimate. So that's compositions composed of primes. So again, you can look at page 298, 299 of the book to see some of the interesting calculations that I omitted. This one isn't necessarily quite so simple as the other ones that we've talked about. And then there's partitions from a fixed set, which are called denumerants. So that's a famous example of that is how many ways are there to make change for n cents. So this, the order doesn't matter, so it's just the set of things that you can choose. So 14 cents, you can either take 14 pennies, or 9 pennies and a nickel, or 4 pennies and 2 nickels, or 4 pennies and a dime. There's 4 different ways to make change for n cents. And for 14 cents. For 15 cents, there's 6 different ways enumerated here. But this is easy with analytic combinatorics. The construction is a multi-set of pennies, nickels, dimes, and quarters. The symbolic method immediately gives a generating function equation, 1 over 1 minus z to the fifth, 1 minus z to the 10th, 1 minus z to the 25th. That's a polynomial, a complicated polynomial, but it's a polynomial. That's, again, a meromorphic function, a ratio of 2 analytic functions. What we're interested in is the zeros. In this case, we have a higher order pole at z equals 1. And this is the plot of this function. It kind of mixes up the roots of unity. But there's at 1, there's a pole of order 5. So we have to do a more complicated residue calculation. In this case, it's easy to show with the limit form of the coefficient calculation that since 1 minus z over 1 minus z to the t is equal to the sum of these things, then the limit is just 1 over t. So immediately get out the result that the coefficient is 1 over the product 1 times 5 times 10 times 25th. And it's a pole of order 4, that's a typo. And so the asymptotics of the coefficient is n cubed over 7,500. So again, quite easily from the symbolic method, we get combinatorial construction, generating function, asymptotics of coefficient. In this case, the estimate is not exponentially accurate because there's an n squared term and so forth. And also the other poles are not so far away. So this one, n has to be larger for it to become accurate. But still, we can calculate more terms if we want and so forth, depending on how much calculation. Our meromorphic transfer theorem actually gives an exact equation for it, and then we can do asymptotics on that. But still, and again, if you want to choose different coins or whatever, you can go ahead and immediately get asymptotic results for comparison. So that's more examples with compositions and partitions showing how the meromorphic transfer theorem gives us, via analytic combinatorics, very high-level derivations from combinatorial constructions right through to asymptotic results.